Welcome to part 3 of our lecture series on using our Raspberry Pi Plus camera to create our very own QR code scanner. In parts 1 and 2 of this lecture series, we explored the history and development of QR codes, and then we developed an algorithm on our Raspberry Pi to detect the presence of a QR code in our camera field of view and to decode the information contained within the QR code and print that information to the screen. In part 3 of this lecture series, we'll take a look at a case study, specifically the use of QR codes in robotics. Shown here is an image of an Amazon warehouse, a standard Amazon fulfillment center, with a small army of Amazon robots traversing the floor of the warehouse. Each robot is constantly moving along the floor of the warehouse, identifying, locating, and moving these shelving units, inside of which a variety of products are located.
For a glimpse into the future, consider one of the largest companies on the planet, Amazon.
Amazon has tremendous scale. We have fulfillment centers that are as large as 1.25 million square feet. That's like 23 football fields. And in it, we'll have just millions of products.
To deal with that scale, Amazon has built an army of robots.
Like a marching army of ants that can constantly change its goals based on the situation at hand, right? So our robotics are very adaptive and reactive in order to extend human capability to allow for more efficiencies within our own buildings.
And there's plenty more where those came from. Every day, this facility in Boston graduates a new batch of machines.
All of the robots that you see that are moving the pods have been built right here in Boston. I call it the nursery, where the robots are born. They'll be built, they'll take their first breath of air, they'll do their own diagnostics. Once they're good, then they'll line up for robot graduation, and then they will swing their tassels to the appropriate side, drive themselves right onto a pallet, and go directly to a fulfillment center.
You may have noticed in the preceding video, the floor of the Amazon warehouses are littered with these QR codes. And it's the information encoded in the QR code that is read or perceived by each robot, and that information permits the robot to localize itself within the warehouse and utilize that ability to localize itself to drive the product from one area of the warehouse to the next. In this sense, then, the ability of the Amazon robotic platforms to perceive the QR codes and digest and utilize the information encoded in each QR code is vital to their business model and the success of their warehouse operations. Let's take a look at another robotic platform. Here I'm showing an overhead view of a small four-wheeled robot, and this robot is autonomously traversing a Grand Challenge course. This, in fact, is the robot that is the focal point of my graduate robotics course. As part of this case study, we'll take a look at utilizing QR codes to control various aspects of this robotic platform. Here's a close-up view of the robot. Again, it's a four-wheeled robot. Here we have a 360-degree field of view camera mounted at top. This robot is controlled with a Raspberry Pi. We use the Raspberry Pi camera for perception to view what's going on in front of the robot. And mounted to the front of the vehicle is a robotic gripper. That robotic gripper is composed of a standard servo motor and a variety of 3D printed parts to form the gripper. Here I'm demonstrating the use of QR codes to control the position of the gripper. The camera connected to the Raspberry Pi in front of the vehicle perceives the presence of a QR code. The Raspberry Pi algorithm decodes the information contained within the QR code, and then we use that information to command the servo motor This in turn controls the position of the robotic gripper. Here I'm showing 3 different positions: fully open, halfway open, and fully closed. Let's dive deeper into this control algorithm and take a look at how we're utilizing these QR codes to control the position of this robotic gripper. The servo motor mounted inside of this robotic gripper is controlled through the use of the GPIO pins on our Raspberry Pi. GPIO stands for General Purpose Input Output, and you can think of them effectively as digital pins. They're either high at 3.3 volts or low at ground. These pins can be controlled by the user through software and enable a variety of applications, such as the generation of pulse width modulated outputs, I2C protocols, and serial communications. Here is a pin diagram of the GPIO pins on a standard Raspberry Pi. You'll notice there are 40 pins, 1, 2, all the way down to 39, 40. And I'm showing the physical layout of the pins on the board here. So if you were to look at your board from the top down, pin 1 would be this top left pin, and pin 40 would be this lower right pin. You'll notice there are 5 volt and 3.3 volt rails available for the user, and then there's a variety of ground pins as well. As I mentioned before, the outputs of the GPIO pins are either 3.3 volts high or ground. So each pin here, denoted as a GPIO pin, can only output 3.3 volts or 0 volts for ground, even though there are 5 volt rails available. These general purpose input-output pins can also be used as inputs, reading in, again, 3.3 volts or ground. And for the details on this pin diagram, feel free to type pinout in a terminal window and hit enter. I'll also mention that a variety of hats are available for the Raspberry Pi GPIO pins. Here's a nice one that tells you the pinout diagram. You can just lay this directly on your Raspberry Pi and utilize this information. The robotic gripper is composed of a standard servo motor along with a variety of 3D printed parts and attaching hardware. Here's a completed assembly of the gripper, and you'll notice based on these arms with geared teeth here, the position of the robotic gripper, this being fully open, this being fully closed, is entirely dependent on the angular position of the servo motor. So our ability to control the position of the servo motor allows us to control the state of the robotic gripper. Here is the wiring diagram for the servo motor. A standard servo motor has 3 inputs. We have a red wire here for power, we have a brown wire for ground, and we have an orange wire here for signal. Now you'll notice the servo motor that we're using in this robotic gripper also has 3 inputs: black for ground, red for power, and yellow for that input signal. So that yellow wire is going to connect our servo motor to the GPIO pin that we will use to control the position of the motor, and through the mechanical linkages of our robotic gripper that will control the state of the robotic gripper. The control signal that will generate on the GPIO pin will be a pulse width modulated output. And when it comes to the control of a servo motor, the primary aspect of the control signal that we are focused on is the duty cycle. And the duty cycle of any signal is the time high divided by the full period of the cycle. It's very standard for servo motors to operate with a period of 20 milliseconds. So that'll be a 50 hertz pulse width modulated signal. For this particular servo motor, a duty cycle of 5% will drive the motor to the full left position. A duty cycle of 7.5% will drive the motor to the full center position, and a duty cycle of 10% will drive the motor to the full right position. Now these are the numbers that are provided in the datasheet for this particular motor. We see that when we build the robotic gripper, due to tolerancing, each motor is slightly different, so we'll have to adjust these numbers accordingly. With our robotic gripper assembled and wired, we'll enter a Python 3 shell and import the GPIO library. So that'll be import rpi.gpio as GPIO. This capital GPIO then being the alias that we'll use for this Raspberry Pi GPIO library. We need to define the GPIO pin as an output that we'll be using to control the position of the servo motor. So on physical pin 36, I'll define that as an output. First step then is I need to tell the Raspberry Pi the configuration of the board. So I'll go ahead and run a GPIO.setMode, and I'll run that as GPIO.board. That will tell the Pi to use the physical pins to denote the layout of our GPIO pins. We'll then come in and we'll set up that physical pin 36 as an output. So that'll be a GPIO.setup, 36 being the pin number, GPIO out denoting an output on that pin. We'll be outputting a signal with pin 36. We'll then come in and we'll define that PWM signal, that pulse width modulated signal. Recall we require a frequency of 50 Hertz, a period of 20 milliseconds for this particular servo motor. So we'll set PWM equals GPIO.PWM. So we'll use the PWM functionality inherent in the GPIO library. And we'll define on pin 36 a PWM signal at a frequency of 50 Hertz. Let's go ahead and start the PWM signal at a duty cycle of 5%. So PWM.start, that will initialize the output of a PWM pulse width modulated signal at a duty cycle of 5%. Again, that being time high divided by the full period of the cycle, that'll be equal to 5%, where high will be 3.3 volts and low will be ground. If we change the duty cycle of that pulse width modulated output, we'll drive the servo motor to different angles and thus will open and close the robotic gripper. So we can run a PWM.change duty cycle, and the input to that function will be the updated duty cycle that we'd like to output to the servo motor. For the robotic gripper I'm showing in this presentation, full left required a duty cycle of 3.5%, full right requires a duty cycle of 7.5%, and then the center position is at 5.5%. You'll recall that's slightly different than the manufacturer's specifications, and that ultimately comes down to tolerancing from one motor to the next. Once we're finished, we can go ahead and stop the output to that pin. So we'll run a PWM.stop. That'll effectively set that pin down to ground, and then we'll go ahead and clean up the GPIO pins. So GPIO.cleanup, that sets all of the GPIO pins on the Raspberry Pi as inputs in an attempt to prevent us from accidentally sending an output signal and damaging something connected to our Raspberry Pi. So now that we have an idea of the signals we need to generate to control the position of this robotic gripper, let's take a look at how we can use our perception system on our robotic platform to perceive a QR code and utilize that information to command the gripper. Using the code generated in Lecture 1, I've gone ahead and created 3 QR codes as presented here. At left, I've encoded the word close into this QR code. At center, I've encoded the word half, and at right, I've encoded the word, or the string I should say, open. These all refer to the state of the robotic gripper. So if I want to close the robotic gripper, I need to generate a pulse width modulated signal on my GPIO pin with a duty cycle of 3.5%. That refers to the numbers that we coded into our change duty cycle algorithm. To command the robotic gripper halfway open, I'll generate a PWM signal with a duty cycle of 5.5%, and then to open the robotic gripper fully, I'll generate a signal with a 7.5% duty cycle. So in each QR code, I'm encoding a string, and then based on the robotic perception of that string, I'll write an algorithm that will change the duty cycle of that pulse width modulated output, thereby effectively changing the state of the robotic gripper. To begin, I'll copy our QR code 01.py script generated in earlier lectures and modify that script. So here I have a copy that I refer to as QR code 02.py, and I'll sudo nano into that script. As you see here, this script is largely similar to QR code 01, except that now I've imported that rpio.gpio library, enabling me to command the state of each GPIO pin. I've set up the GPIO pins according to gpio.board. That's the physical layout on the board. And I've identified pin 36 as an output. I'm going to use pin 36 to generate that control signal that I'll send to my servo motor. Here I define the PWM signal that'll be on pin 36 with a frequency of 50 Hertz, and I initialize that at 5.5% duty cycle. As was the case with QR code 01, I will open up my video capture and define my QR code detector, and then I enter an infinite loop here where I'm constantly attempting to detect the presence of a QR code. In the case where a QR code is detected, I'll draw the bounding box around my QR code, and based on the data, based on this case the strings that I've generated, I'll use those strings to define the duty cycle with which I'll change the pulse width modulated signal. So in the case where the string is half, I'll change the duty cycle to 5.5. Where the string is open, I'll change the duty cycle to 7.5. And then where the string is closed, I'll change the duty cycle to 3.5%. So by updating this QR code 01 script and adding in this functionality, I can now perceive a QR code, I can decode that information, and I can use that information to command my robotic gripper. One other addition here, to exit this infinite loop, I have a wait key for a key press of lowercase q, and when I press lowercase q, I'll go ahead and stop that PWM output and clean up my GPIO pins before I break out of this script. So here is that QR code 02.py script in action. I have 3 different QR codes. In this case, I printed them out on 3 pieces of paper. When I place the QR code in the field of view of the camera, the algorithm detects the presence of the QR code and then decodes the information contained within that QR code. In the case where the string open, close, or half is identified, the algorithm commands the robotic gripper to that state. You'll also notice that I'm printing this information that has been encoded inside of the QR code to the terminal window. This functionality can then be utilized for both the control of the robotic gripper as well as the vehicle itself in terms of controlling the wheels. So if we were to place QR codes around the Grand Challenge Arena, we could use that to localize the vehicle, and we could use that information to command the vehicle to drive to its next position. In a similar fashion that the Amazon warehouse robots are utilizing QR codes spread across the floor of the warehouse to localize their position and then command the vehicle to drive to its next destination. That wraps up part 3 of our lecture series, taking a look at how to use our Raspberry Pi Plus camera to create our very own QR code scanner. In this lecture, we evaluated a case study where the perception subsystem of a robot consisted of a Raspberry Pi Plus camera utilized to detect the presence of and decode information contained within QR codes in its environment. As always, if you have questions or comments, please reach out to me anytime.